Hey everybody, welcome to another edition of the Atlanta.net Users Group. Our speaker for tonight is Jason Farrell. He's a senior consultant with me over at Microsoft and an expert on all things graph database and Kubernetes and a whole bunch of different stuff. So Jason, I'm going to turn it over to you.
All right, well, thank you, Ken. First off, everyone, pleasure to be here tonight. It's my first user group presentation in quite some time due to, you know, the thing. So very happy to be here with everybody tonight. I'm actually going to change my screen for a second so I can see if somebody is talking. So the format of the presentation tonight is I'm going to go ahead and give it. If you have any questions throughout, please do not hesitate to stop me and ask. Just raise your hand and I'll call on you. But the topic for tonight is graph databases. I guess by a show of hands or coming off of mute, whichever you prefer, who has experience with graph databases, not GraphQL, graph databases, that they would like to kind of just share?
So this is Jason. I did do some work with graph databases maybe 2 or 3 years ago when it was fairly new during my my master's in data science. I haven't touched it since, but I have a good idea what it does.
Which platform were you using at the time?
I can't remember, to be honest.
That's okay. Just curious. Yeah, data science is definitely an area where graph databases are finding more and more usage. And we'll kind of just touch on that in this talk. So, well, thank you, Jason, for sharing your experience. Really do appreciate it. So let's go ahead and get into the talk. I'm not on the right screen. Here we go. So as Ken mentioned, Jason Farrell, senior consultant. I live up here in Suwanee, Georgia, just a little bit of ways away from Ken. There's the blog, Twitter, and my GitHub. So the GitHub will contain all the source code for the demos we'll be doing tonight, as well as other things out there. So without further ado, let's go ahead and get into the talk. Databases. Well, you got to have one, probably, maybe more, who knows. So part of this talk is discussing a certain kind of database and maybe even Excel, who knows. But as we start talking about this topic, I always feel it necessary to dive into a bit of how we got to the point of where we needed graph databases to be a thing. So we can go all the way back to the 1960s or 70s and find the fundamental birth in the RDBMS. So the relational database management system, data is organized into tables, columns, and rows. It's very human readable. And the major advantage of this was it was normalized to really save space. As many of us probably know, space was pretty expensive up until about 20, 30 years ago, and then it became cheaper. So the idea of normalization to avoid repetition was key to ensuring that you didn't make something that was too expensive. Now, the key thing with a RDBMS tends to be its emphasis on consistency, particularly through an ACID transaction, atomic, consistent, isolated, and I believe it's dependent. I forget what the D stands for. Transactions, meaning that when a read against the database is made, the state of the database is always guaranteed to be consistent. So that's what that is. Now, key thing is when we're designing systems that deal with RDBMSs, the data in those systems tends to be organized based on our comprehension of the data itself. So we have tables like person or color or city, those types of things. So, but the underlying problem with an RDBMS is it was designed for vertical scalability. It wasn't so much designed for horizontal due to the emphasis on consistency. So as we kind of move forward and we're not able to vertically scale as much, a new database system arose, which is NoSQL. Now today, NoSQL covers a wide variety of different subtypes, one of which is graph. But the key use case for NoSQL is an ingestion scenario, meaning you're taking in a bunch of data, where as part of its emphasis on consistency, an RDBMS enforces certain schema on the data that's coming in. NoSQL often does not. And this is intentional because we're going to go for something called eventual consistency in most cases, meaning it's at the other end of the spectrum where we will not guarantee that the data is consistent. And because it's not structured, we don't typically use it for long-term storage. It's more of an ingestion mechanism. And because the cost of that can be a lot higher when compared to an RDBMS. Now, the crucial thing is, again, we talked about with RDBMS, the data is organized for humans. In NoSQL, it is organized for the application, meaning when you organize your data for reads, you're going to do so based on how the application is going to use your data, not necessarily how you organize, how you perceive the data. I find that's a common problem a lot of teams have when they first start using NoSQL, and it plays into graph very, very well, is that they organize it based on how they view the data, which is very much an RDBMS trait. In NoSQL, you want to organize the data based on how the application reads the data more specifically. So, but that's kind of where we started at and kind of why these two SQL databases emerged. But there was always this, well, which one do I use? And I don't know, I'm curious if anybody out there has ever heard of the CAP theorem by Eric Brewer. Anybody? Nobody? Really? All right, well, Eric Brewer, who today is, I believe, a distinguished engineer at Google, in 1998, he wrote his paper on the CAP theorem, which he suggests that databases can emphasize two of three traits: consistency, availability, or partition tolerance. Now, he argues that because of the mechanism of horizontal scaling, all databases need to adhere to the P, which is partition tolerance. Thus, he surmised you will only ever have a CP, a consistently partitioned database, or an AP system, which is highly available and, again, partition tolerant. So this was actually known as the rule of two, which turned out to be more of a guideline. The reason being is over time, what we've come to understand is that database systems can have all three, but they can have them in different degrees. For example, Cosmos DB, if you take a strong consistency model, it's basically like in our DBMS. It's highly consistent on the reads. However, if you set the consistency model to eventual, it's effectively a pure AP database. If you set the consistency model to session, it's kind of in the middle. So it would actually kind of be right in here. Out of curiosity, who here has worked with Cosmos DB in the past? Samrak, if you're talking, I can't hear you. Excellent. So there's a wide variety of systems that kind of are starting to follow this. DynamoDB is one, the Spanner from Google Cloud, and Cosmos DB, among others. This idea of the rule of two is more of a guideline. So it is within that realm that graph databases are featured as kind of an AP database more so, but also a CP database, depending on how you choose the consistency model. So what is a graph database? Central question as we kind of get into our conversation here. Well, put simply, a graph database is a database that's built on what is called graph theory. Graph theory is an element of discrete mathematics that looks at the way problems can be represented using graphs. Now, in the computer sciences, these graphs are very, very common. linked lists, and B trees are just two of the examples that use a graph nomenclature to represent the structure of things. Probably I'm losing the word here. Probably the most obvious candidate for graph databases is something like a mapping application. So I'm curious if anybody here has ever heard of the traveling salesman problem. Anybody? Tim? Okay. All right. Well, so the traveling salesman problem is a question from the graph theory, which postulates that given a map of the continental United States, 48 contiguous states, and a salesman who is tasked to visit each state, what is the most efficient path that salesman could take to visit all 48 states? So the relationship between the states is represented as a graph with vertices and edges. And the various weights on the wedges will help us determine what path that should take. A common way to solve this problem is Dijkstra's algorithm, where it kind of takes into account the weighting across multiple paths. Now, in that kind of a situation, this graph would be what we refer to as a directed graph. Directed graph means all edges point in the same direction. A great example of this in computer science is a B tree, where you start at the top and then you're going down. You're always traversing downward, never back up. Whereas a linked list would be considered an undirected because you can go either way. It's a connecting point. So that's kind of how a graph database gets its data. The data is represented as a vertex, and its relationship to another vertex or data is represented by an edge. Does that make sense to everybody? I'm a very two-way person, so please, I'm going to ask questions. So.
Yes.
So let's kind of take this to another level, and we're going to start kind of getting more practical. So if we consider the fact that we wanted to represent the relationships between people. So for example, my son Ethan is a person, and he is my child. We might represent this with a child of edge that connects Ethan to me. So the edges and the vertices in a graph database can have key value metadata, which allows us to associate different things. It can even inform our decision-making process as we start to traverse the graph. So a great example might be if you're building a mapping application. You might choose to have metadata on the edge that represents the amount of traffic congestion between two intersections. Thus, if you're doing a mapping exercise, you may try to avoid that edge because it will slow down your transit of that particular route. So now, what's curious about this is as you kind of dig into this, you'll find yourself very commonly thinking about relationships in the reverse of how you might think of it otherwise. For example, typically how we think of mapping this in a traditional database might be, well, let's list the parents, list the children, and the children will have a parent ID column. And that works perfectly well. And I want to make very clear that graph databases are not offering the ability to do something that cannot be done with existing systems. It's just a different way of looking at things. So in the traditional sense, we might give each child a parent ID column that is then null when we're at the top of the tree. However, in a graph database, we might have a parent, and then that child will indicate from it who its parents are. So it can kind of be reversed in that sense. So go ahead, Johnson. So. Johnson Singh, did you have a question? If you are speaking, I cannot hear you. Oh, is there a question in the chat maybe?
I could see that he unmuted, but it's not hearing his audio.
Yeah. Oh, there's some stuff in here. JetBrains. You're talking about JetBrains. Okay. What's the advantage of that? So, Johnson, that's a great question, and that's actually what the next slide is about. So let's kind of talk about, in this, I would be fully transparent in this particular instance, it doesn't really give you much benefit. However, let's look at a different example. Let's consider a situation like Facebook, okay? You have created a post that you wish to then calculate how many people have liked it. Now, there are many ways to do this in a traditional sense. Typically, what you do is you create a flat table with no normalizations, and you just do counts. You can definitely do that. However, in a graph database, instead, the user liking your post is represented explicitly. Then, when you go to the post vertex can count how many edges of a particular type are associated to it without traversing. So that's very powerful, because in the traditional model, we would have to kind of do a complete table scan to figure out all of our particular values. Whereas in the graph, we're just looking at the number of edges on our vertex. So in that sense, this becomes a bit simpler. And you can see why graph databases are very attractive to places like Facebook or Twitter, or really any system where the relationship is more important than the data itself. You know, Facebook is a good example of this, in that it's great to have all these posts and whatnot, but what Facebook is after is who liked what, who commented on what, and that sort of thing. And what can you traverse from that and understand about somebody? Does that answer your question, Johnson, a bit? Or did you, I mean, we can, I want to be really clear on this. We can keep kind of talking about it a bit more if you want.
No, I think I'm good for now.
So yes, in the parent-child situation, you know, it's such a easy, you know, an easy data model to conceive. It's fine. But in this case, where I would fully admit there are ways to do it in traditional, you can definitely create a flat table, but you will still have to query scan that entire table. You can do some magic with indexing and whatnot, but at the end of the day, you're going to have a very long table. Whereas in the graph notation, you're going to have users making a relationship edge to your post, and then the post can simply say, well, how many of these type of edges do I have associated to me? So it becomes a bit simpler. Does that make sense to everybody?
Yep.
Oh. All right. All right. So now that we've kind of got a handle on why a graph database may make sense for certain scenarios, let's talk about examples of real life graph databases. What time is it? Okay, cool. Running good. So the two main engines out there for graph databases are Apache Tinkerpop and Neo4j. I would be willing to bet many people here have heard of Neo4j. It's a pretty popular product. It also supports GraphQL, which, for the record, GraphQL has nothing to do with graph database, just as a word. So Neo4j, the biggest difference is Neo4j is an enterprise platform and it's proprietary, it's closed source. Apache Tinkerpop is an open source platform from the Apache Foundation, and it's the one we're going to focus our time on tonight. So what is it? So Tinkerpop is an OLAP database, OLTP, I'm sorry, that essentially supports a graph querying model. The language used to query that database is known as Gremlin. So what I pasted here is an example of a Gremlin from JavaScript. So this is what it looks like in JavaScript if you were to use it. But you can see that the language structure here, it's very much designed to mimic graph queries themselves from mathematics. We have a match, and what you're seeing here is you're seeing traversals. The gremlin is starting at is looking at all vertexes and then asking, based on a traversal, which ones map to its criteria, which here are what projects have or have creators that are both friends, essentially. So the out in this situation is a type of relationship, just to be very clear. So if we look at gremlin a bit closer, it's not a very hard language to it's very much related to kind of like an ETL process. As you start at a vertex and you move to another vertex, you're kind of doing a sort of transformation process. You're taking the data, making a decision about which edges to follow from that point. And that will kind of fan outward as you go based on the structure of your query. Now, the important thing when you're doing these kind of queries is understanding whether the graph itself is directed or undirected. And also understand that a graph itself does not have to be one or the other. The relationships within that graph can be directed or undirected. For example, one of the ones that you're going to see later is a person liking an artist is a directed relationship. The person's always going to like that artist. The artist is never going to like the person. However, if we again draw on social media, if you've got a Facebook friend, that person is a friend to you and you are a friend to them. So it's undirected, meaning it can go both ways. So that's the key point to understand when you're building these relationships. Because if you're going to do undirected, you have to do both. You must provide the downward edge and the upward edge. Questions on that? Okay. Moving forward. So that gets us into Cosmos DB. So Cosmos DB, we do support graph databases under the Gremlin API. And it is a managed version of Apache Tinkerpot. So when you do this, you get all the advantages of Cosmos DB. You get the global scale and adjustable consistency settings. Like we talked about earlier, it allows you to blend the best of consistent databases with a highly available database as well. Now, one thing that the team did request that I mentioned to you when I was reviewing this with them is queries in Cosmos DB are time-bound, and they rely heavily upon the allocated throughput that you give your database. Now, in some cases, graph queries can be quite heavy and take time because depending on how many vertexes you are traversing. If you exceed that, if that time exceeds your throughput, then you'll have issues with the results coming back because you will have, each time you are going to another vertex, you're effectively making a query. So the Cosmos DB team asked me to kind of make sure I mention that and make sure that that's clear as I was presenting this. So are there any questions regarding this point? All right, move on. So earlier we talked about being available and database. One of the most key parts of Cosmos and any partition database like Cosmos is the selection of your partition key. So much like any of the other database types in Cosmos, the GraphDB relies upon a partition key to quickly find vertices. So again, going back to what we said, depending on how you're going to query your first vertex based on what data you want to start with, that should inform your partition key system so that as it's scanning those partitions, Gremlin has less to look at in that particular without crossing partitions. Is everybody familiar with how partition keys work in Cosmos DB? Okay. All right. So one of the tips I'll give you if you decide to use this is when you create a vertex, use vertex as a base class and to inform and enforce that the derivations implement the partition key appropriately. Just because if you don't do this properly, then your queries will be a lot slower, which is typical, which is the same is true with any of the other APIs in Cosmos as well. All right, moving forward. Oops, wrong screen. So let's go ahead and create a graph database in Cosmos DB. So I'm going to do this through the portal. So bring this up. So I have a resource group right here, and we're going to go ahead and press create. Type in Cosmos and take the Cosmos DB. So right now we're on that screen, and I'll hit Cosmos DB create. So you can see it's right here. Apache Tinkerpop using the Gremlin query language. I'll hit create. It's going to ask me a few things. I'll call this Cosmos-Gremlin test YM01. And we'll put this near me in East US too. I'm going to use the serverless capacity. You can use provision throughput as well. It's kind of up to you. I'm not going to do availability zones. I'll leave the network as public. And take the default backup policy and use a service managed key. So I'll do that. And I'll hit create. This doesn't typically take very long, but I'll let it kind of go for a little bit. And does anybody have any questions to this point so far? Really, no questions. All right. So while that's kind of going, let's kind of jump back over here. And I want to wait for that to finish so I can show it to you. So what I'll do is I'm going to go home and I'll go into the one we're going to use later. So this is one that I've already created. So much like a lot of the other databases in Azure, we have keys, we have identities, but we have this data explorer as well. So the nice thing about Gremlin is they give you some really good visualization tools. So for example, I can go in here and I'm going to run a query of g.v. Just it says, give me all the vertices and their related edges. So run that, and you can see I have one entry in here. Oh, I have multiple. So you can kind of see what it's doing is it's actually showing me these are all the relationships between various artists. I actually have another tool that I can show as well. This tool is called GDOTV. Waiting for it to come up. Actually, it has. All right. There it is. All right, come on. So the nice thing, again, this kind of gets into the whole visualization of databases. So let's do a new query. And I'll go in here. And we'll hit play. So now this tool, GDOTV, it gives you a really good JSON, but what I like is the graph view. So you can kind of see all the relationships that are kind of going on in this particular database. So it kind of says like there's a friend relationship here, and then there's a liking of artists all over the place. So go back to Azure. And you can define things like store procedures and UDFs in here as well, and triggers. So it works the same as in the other Cosmos APIs. It just has graphs and vertices instead. So that's how you create an instance of one. Let's keep going. Okay. So this is always the seminal question. When should you consider a graph database? And it's really a hard question because you want to avoid viewing a graph database as a general purpose database, because it's not. But there are some pretty interesting use cases. We've talked about a few of these, like map applications. One of the exercises that I'm currently working on in my spare time is mapping my area around me here in Georgia to kind of play with like a navigational system. How might I navigate to a given location while avoiding traffic, as an example. Another one that's really becoming popular is what's known as AI learning systems. So when you start talking about AI and building neural networks, it's about how the actual data is related to each other. And so if you hear a bunch of noise, it's my son trying to go to bed, which is always hilarious. AI learning systems. So you can have the traversals of these relationships and let AI kind of map those relationships. Another one is product composition. So for example, your refrigerator at home or some other appliance, you could represent all the internal parts as a graph. And using the graph, it can report on, okay, well, how fast, how well is something working? And depending on when something's about to fail, you can do predictive failure models to determine when a new part needs to be replaced. Another one would be a family tree, a recommendation engine where, again, similar to AI, we're looking at that relationship between elements to determine what we should recommend to people. So those are a few of the ones that I kind of came up with. Anybody else have any they want to come off mute and share? Anything else that they kind of think to themselves, would that work for graph? Well, I'll share one that we've been kind of debating here at Microsoft, actually. So one of my current clients is a big insurance company. And the way that they operate today is they have these JSON files that define their insurance products, because insurance products are different depending on your state, your municipality, what you're insuring. But there's a lot of problems with that, because if they make a change to the national level, they have to update thousands of products. So they're trying to get away from that. So what we're exploring is, could we build a graph database that would allow traversal to actually build a product instead of their current model? So there really is a lot of interesting use cases to graph databases that I think is worth exploring. Okay. So with that in mind, I want to show you a recommendation engine. So I built a recommendation engine out of using some music stuff. So I'm gonna bring that up really quick. And I apologize, it's not sort of, it's a rather, yeah. And you'll find this application in, oops. You'll find this application in my GitHub repository. Okay. So what it's going to ask me first is give me some options once it compiles up and everything. Okay, I'm going to see the I'm going to clear out the database and reseed it just to be okay. Okay, cool. So I'll rerun this query. And we'll do graph view. All right, so now this is the starting point of it. So I am friends with my wife, Claire Farrell. So I want to see, so I like Metallica, which is rock and roll, and Goo Goo Dolls, which is alternative. She's Korean, so she loves BTS. So it's the pop group. So now if I ask for a recommendation based on being her friend, this thing, my engine, which is very simplistic, is going to look at me and say, well, it's going to suggest different things depending on the situation. Let's see what it suggests, what it's going to actually suggest here. So we'll do 5. I want you to make a recommendation for me. Okay, so it's saying, because you like Metallica, you might also like Skillet because they're rock and roll. So just picked a random one out of the rock and alternative ones. So if I hit yes on that, it makes the recommendation. If I play again, I now have this recommendation. Now, let's mutate this a little bit. Let's create a new user. So we'll go ahead and do 2. We're going to do Ken Ross. And then we'll have Ken like Taylor Swift. I'm sure he loves Taylor Swift. Okay, so now Ken likes Taylor Swift. Okay. All right, so he likes Taylor Swift. Now, he's not friends with anybody, so if I ask for another recommendation, I believe it's going to pick either BTS or NSYNC. So let's make a recommendation for Ken. I'll get NSYNC because it sees that he likes Taylor Swift, who is pop. So it says, hey, you probably like other pop artists. Cool. Now, let's make Ken friends with my wife. So Ken, you're friends with my wife. Okay. So now Ken likes pop. So does my wife. So if I play this again, can anybody guess if I do a recommendation for Ken this time, who's it going to recommend, do you think? Yep.
BTS?
We'll see. I think so. I think you're right, though. Yeah. Again, this is a very basic one, so I didn't, it's not like hugely sophisticated. But the idea is it's traversing the graph. It's Skillet, actually. Now, why Skillet? I'm not actually sure why. I was not expecting that. All right. So again, here, I think it's looking. Okay, it traverses all the friends and says, well, you've got 2 of these. We see some more rock and roll out there. Maybe you like Skillet. So let's say he doesn't like Skillet. Let's do 5 again. Let's recommend for my wife. Now it's suggesting to her Metallica because she likes BTS, but then it's just picking Metallica out of here because I like Metallica. So let's go ahead and give her and say, yes, I'll take that recommendation. And then let's do, I'll have her I'll have Ken like George Strait. So now I'm throwing him off beat here a bit. So now we look at the database and Ken likes George Strait. So this time, let's see here. I would guess it's Pop Evil probably. So let's make a recommendation for Ken. Pop Evil. Now, how did I know that? I was actually completely a guess. Because it picked Metallica last time, and I happen to know that's rock and roll. So we'll take that recommendation. So what we can do now, though, is I can say, well, I want to get some information on the artist. So the user. So let's say Ken. So Ken has one friend, that's Claire, and he likes 4 artists. Cool. And then let's get artist info. So we'll do that. Do Pop Evil. So it's Pop Evil. The genre is rock. So anybody now does anybody want to actually kind of walk through this and have me do one that I might not be part of my script? Now, actually, I should probably point out how this is working. So let's look at some code here. So we'll bring up VS Code. So the way this process works is I have these sort of commands. Let's look at the recommendation. So the recommendation receives iQuery source and iRecommendation engine. Now, query source is my abstraction on top of Gremlin. And it's using a library called xram gremlink. And that's what allows me to kind of have like link-like queries with Gremlin. So you can see V, I'm looking at the from ID, and then here's the edge. One of the things I talked about was having this sort of base class. So I'm abstracting the ID, which is actually my partition key. So if you go to And you'll be asked this when you create a new database. In your settings, I have item type, I'm sorry. So I have different item types, essentially. Now, the important thing to understand about the partition key when you define it is case sensitive. And despite the fact that most of these tools are going to show you this stuff in JSON, it's not actually being stored in JSON. So if you use something like Newtonsoft or a JSON serializer, it's not the same thing. So lowercase I item type is not the same as item type. Your partition key has to also match in terms of casing as well. Just keep that in mind, because that threw me off quite a bit when I was first getting started. So you can see that I've got different queries up here. Here's a double-edged vertex where I'm actually looking at edges going both ways, going out or coming in. And all this is very similar to any kind of graph query you would do in general with either the standard library or in mathematical terms. So what happens is if I come back to, down a bit. If I come back to the command, recommendation command, what happens in here is I gather some data. I say, give me a user, and I ask the recommendation engine to give me a user based on the selected user that came back. So if I do that, let's go into the recommendation engine. What's happening here is I'm getting all the liked artists by that user first, and looking at which ones by frequency. So how many, if you like rock and roll more than pop, I'm gonna look for rock and roll artists and whatnot. But the rest of this is all very basic C# code, but it's also talking to the query source pretty heavily. And the query source actually handles all the work of talking to the graph. So any questions on this to this point? Eric, yes, the question is yes. So it's how it stores it is very similar to the document DB in that it's still looking at partition keys. But I have to give you a deeper answer on how Apache Tinkerpop actually does it. But it's, yeah, that's about the best answer I can give you. So again, document databases kind of serve a different purpose than a graph database. They're designed to take in a large document of data. The way that I often look at a graph database versus other databases is, in a graph database, your relationships are the most important aspect of your data, how that data is related. If you're just trying to store data like a lot of applications do, a graph database is not probably the best answer for you. Does that make sense?
Hey, yeah, that makes sense. I'd be kind of curious because I'm looking at your example here, and you really just have a first and last name. Would you, if you were building an application, have a separate place to store more information about Ken, for instance, or would you create a Ken entity in here that's part of the graph that would have address and stuff, phone number?
Yeah. So one of the things that you see a lot happen is a graph database almost serves as a supplement. So you may start at a vertex and get all these IDs, and then you may use that list of IDs to then go to an actual database and get the rest of the data. That being said, the edges and the vertices can also have key value data points. So for example, I could store that Ken has silver hair, or I could store that he has a crazy background, because he does. You know, those types of attributes. So one of the examples I gave earlier was you may have a vertex that's an intersection, that's an intersection of two streets. What you then also may do is represent the edge as the intersection before it to the current intersection. And within that, you may say traffic congestion is moderate, for example, or heavy. And by doing that, you can then make decisions about which traversal points you want to make. And that gets into the whole Dijkstra's algorithm and weighted edges and how you make decisions, essentially. Does that answer your question?
Yeah, it does. Thank you.
For sure. Whereas in a document DB, you're not really doing that. You're more, I have this data that I'm storing it. And you have a level of importance on those relationships, but the data itself is more important to you than, say, those relationships. Whereas in a system like Facebook or Twitter or even LinkedIn to a degree, it's about that relationship. A lot of social media applications use variants of graph databases for a lot of things for that reason. Very good question. Some property graphs also allow you to assign one or more labels to a vertex or edge. Yes, that's true. And in this situation, what I'm doing mostly is this edge, for example. You can kind of see some stuff. I'm just going off of the label of it. I could add more to this if I wanted to, but essentially what I'm looking at is what type of relationship this is, and that's telling me whether to follow it or not. You could give weightings on this, for example, and they could be dynamic in nature. You could be updating the edges, again, with our traffic example. So there's a lot of things you can do, but I really did mean what I said when a lot of times I see graph databases kind of being the supplement. You may use it to like find things because you want to get all these related data points. And once you have the related data points, you may want to then take those and do a more directed query against like an RDBMS or document database that actually returns all more meaningful data, as an example. Okay, let's go ahead and finish up. All right, so we're almost over. I know it's a late night for everybody, so I appreciate you hanging on this long. I'm sure I can be kind of boring, but anyway. So we always talk about this in software development. Use the right tool for the job. Graph databases are not a general purpose database. And I think that's pretty clear from our discussion tonight. So you want to be very careful when you consider the use case. Don't look at it as a massive, as a storage point for lots of data. I would, again, look at it more as a supplement or a way to express the relationships between data. These are a newer concept, and I'm going to reiterate what I said earlier. I find that a lot of teams have a lot of difficulty understanding how to model data, especially in a NoSQL database, graph or otherwise. So when you're looking at NoSQL, typically you're looking at it from the perspective of how will my application interact with this data set, not how will I perceive it. That's more of an RDBMS type thing versus NoSQL, which is just about the data and the application interacting with the data. Okay. We touched on this a couple times, but graph databases are really more often used in conjunction with other things. So you may traverse the graph to find related data points, and then ultimately take the results of that and do a lookup or some sort of caching. But typically, you do not want your graph database to be your primary storage point for your information. And that's true of NoSQL in general in a lot of cases. The last point I'll leave you with is that graph databases have a great amount of penetration into data science and into AI in particular. Because again, if you think about data science, if you think about AI, we're trying to build data point relationships. We're trying to understand how data is related to each other. And that's where graph databases are really, really well suited to represent. So with that, the source code is all located at that GitHub URL. And there's a link there as well to Gremlink, which is the .NET library I was using. The gentleman who maintains the library is very active and is pretty well known even by the Cosmos DB team, I've came to find. So good library, definitely recommend downloading it and using it. I think it actually is better than the library that comes with Cosmos NuGet packages. All right, so this is the point. Any questions or comments on the topic?
Oh, yeah, I got a question. Where do you see RDF fitting into the graph space?
RDF, help me out.
Triple stores.
Triple stores. I'm afraid I don't know what those are.
It was a subject, predicate, object, I believe.
I think you're getting into an AI related topic that I'm not very well suited to answer. Anybody else want to take that question? Because I'm not sure, unfortunately, Robert.
No worries.
All right. Well, with that in mind, I'd like to say thank you to Ken and the entire, once again, my information. Feel free to contact me on Twitter if you so desire. I'll be hopefully giving this talk in December in Las Vegas. So thank you all for participating in this first run of it. Really do appreciate it. Any feedback, I'm very much welcome. So thank you very much, Ken, and the whole team.
Thanks, Jason. That was awesome.
Appreciate it.
Learned a ton.